Okay, so we are on our ninth episode, which is quite a milestone, guys. We have come to the ninth episode. Now, the question that we'll be covering in this video is incredibly important because it is the combination of of tangents, your center, and it tests our knowledge on a higher level. Okay, it ensures that we have a great understanding on all the theorems that we've learned so far. So please make sure you watch this video very, very, very carefully and let's get started. So 5.2, they tell us in the diagram we have O. O is the center, okay? So O is the center. And just like I've explained previously, I always recommend this. You need to write down a few of the theorems that apply to your center. We know about our radius line. We know about our diameter. We know about line from center to midpoint of chord. And we know about angle at center twice as much as angle at circumference. Okay, now let's first start off by identifying our radius. A radius is a line that stems from your center and touches the circumference of your circle, right? So we can clearly see that OP is a radius, OL is a radius, and OQ is a radius. So all of those lines are going to equal to each other because radii are equal to each other. Okay, radii in a circle are all equal to each other. Now, the minute that we've marked it off, guys, we can clearly see that opposite angles equal sides is going to be applicable because these two angles are a part of a isosceles triangle. We know that angle P will equal to L2, and you just want to mark them off using the exact same color. We know that angle L3 plus L4 is equal to Q1. Okay, just pay very close attention, guys. It's OL that's equal to OQ. So therefore, L3 plus L4 will equal to Q1, not just L3. Okay. Now, let's continue on. We've identified our radius. What about our diameter? A diameter is a line that it passes through our center, touching both ends of our circle, touching both opposite ends of our circle, which is the circumference of the circle, okay? Now, what do we need to know about a diameter? A diameter is a line that subtends a 90-degree angle. Okay, so what does subtend mean? To understand the whole concept of the subtending of an angle, you need to trace the lines that come from that line. Okay, so it is when a line holds another angle to the point where it touches the circumference of the circle, and the angle that it subtends to the point where it touches the circumference of the circle is equal to 90 degrees. Okay, so PQ is definitely our we can clearly see it's definitely our diameter, right? It's definitely our diameter because it passes through the center, touching both sides of the both ends of the circumference of the circle. And remember, guys, diameters are made up of two radii. The two radii that it's made up of would be OP and OQ. So now let's trace the lines that stem from the diameter all the way to the other end of the circumference of the circle. Trace it, trace it, trace it, trace it, trace it, trace it. It ends over there. Trace it, trace it, trace it, trace it, trace it, trace it. It's all the way over there. Okay. So it ends right here by L2, and on the other side, it ends right over here by L4, meaning that L2 plus L3 plus L4 will be equal to 90 degrees because of um, angles in a semicircle. So I'm just going to mark that off. L2 plus L3 plus L4 is going to equal to 90 degrees. Okay. So now, guys, we've identified our diameter. Let's continue on. What about line from center to midpoint of chord? Now, pay very close attention to this theorem. Now, this theorem only applies to a diagram where we have a line that stems from the center and it touches a chord, but that chord would already have had to be split into two equal parts. Okay, so if this chord was split into two equal parts and we had a line that stemmed from the center, then yes, this was going to be applicable. Okay, or it could also be the other way. If we had a line from the center to the chord and I touch that chord and this line was perpendicular to that chord, that's when this theorem would also be applicable. There's a reason why it's called line from center to midpoint of chord, because the point of contact needs to be the center of that line. We know that that point of contact is the center of that line if there's a 90-degree angle between those two lines, or if that line was split into two equal parts as a result of the line touching the chord, right? But it has to already be marked off, okay? I don't want to see anyone making the mistake of immediately seeing a line immediately seeing a line that stems from the center and it touches the chord, and then they assume, okay, yeah, that's when the midpoint theorem applies. No, there has to be a 90-degree angle between those two lines, or that line, that chord that it touches, has to be split into two equal parts. Okay, now let's continue on. We've seen that, yeah, this definitely doesn't apply. What about angle at center twice as much as angle at circumference? Now, the very first thing that I want you to do is, I want, a lot of students actually don't do this. Okay, this will literally make angle at center twice as much as angle at circumference so easy. A lot of students think and they assume that the only thing that they look for is a bow tie shape, like a bow tie shape, one side of the bow tie being shorter than the other, and the other side touching the circumference of the circle, which is an incomplete, it's incompletely wrong way to do it. It is very ineffective way to do it, because that's not always the case. It's not always that visible. It's not always that easy to see, right? It's not that easily outlined or clearly outlined in the diagram. Okay. The first thing is identify the arc that O1 is subtended by. So how do we identify this, guys? Remember the whole concept of the subtending of an angle. It's the exact same thing. What you want to do is you want to start tracing your lines from the angle to the circumference of the circle. So we're going to start tracing it, tracing it, tracing it. It ends over there. Do the exact same thing on the other side. Trace it, trace it, trace it, trace it, trace it. It ends over there. So we know that it is subtended by arc PL. Remember, guys, an arc is just a curved line. It is a curved line that, in this case, the curved line PL, so arc, it's different from just a line, because a line is straight. However, an arc is curved, it is circular, it bounces, it has grooves to it. Okay, so we know that arc PL subtends O1. So we know that, right? Now, the next thing that you want to do is you want to identify the arc that subtends other angles that are on the circumference of the circle. Let's first start off with N. Take your pencil and trace the lines all the way to the other end of the circumference. So we trace it, trace it, trace it, trace it, it ends over there. Do the exact same thing on the other side. We trace it, trace it, trace it, trace it, it ends over there. So we can clearly see that angle N is subtended by LQ. Okay, so we're looking for an angle that is subtended by PL as well. Now let's start. Let's try from looking for P. Not P. Sorry. Let's look at Q1. Let's see what arc subtends P1. So let me just make that off. Okay, so we're going to start off by tracing the lines from Q1 all the way to the other end of the circumference of the circle. It ends right over here at P. Do the exact same thing on the other side. Q1, trace it, ends over here at L4, and boom, look at it, guys. It literally ends right here. Right here at PL. So it looks like Q1 and Q1 and O1 are subtended by the exact same arc. So what does that mean? That means that the angle at center twice as much as angle circumference will be applicable to this specific question, right? And what we want to do is, just in case we don't forget, just to make sure we don't forget, just to ensure we don't forget, we're just going to make a little annotation of a little symbol, okay? I'm just going to write 2 times. This is going to be represented through the symbol of 2 times. Now, remember, our center is split into 2 parts. So you want to try this method, and you want to see if angle at center twice as much as angle at circumference is applicable to the other part of our center, okay? Do the exact same thing. Trace the lines from O2 till this part. Okay, so it ends right over here at LQ. Trace our lines from O2 all the way to the other side. It ends right over here. That means it is subtended by LQ. Now let's do the exact same thing to another angle that is on the circumference of the circle. We're going to try that off with P. Trace the lines, highlight it, trace it, trace it, trace it all the way to the other side. It ends right over here at L. Do the exact same thing on the other side. Trace it, trace it, trace it, trace it. It ends right over here at Q, meaning that it is subtended by LQ. So that means they're subtended by the exact same arc. What does that mean? That means angle at center twice as much as angle at circumference will be applicable to both P and O1. P and O1 is where it's going to be applicable. I'm just going to write it 2 times over there. And then we also saw the fact, we also verified that O1 and Q2 is where it's also applicable. Okay. Now, guys, we're completely finished and we're done with seeing and covering, reviewing, and exploring all of our center theorems. Let's continue on. What about RLM? They tell us that RLM is a tangent. We're going to write down all the theorems that are applicable to our tangent. Okay. So we have tangent from the same point. We have tan chord. We have tangent perpendicular to radius. Okay, so now the only way tangents from the same point would be applicable to this specific question is if we had two tangent two tangents that stem from the same point that touch this part of like the circle. Okay, but in this case this is not the case. Okay, so it's not applicable. We don't even have two tangents, so that's not applicable. What about our tan-chord theorem? Now with the tan-chord theorem we need two things. We need two factors. We need a tangent and we need our chord. So let's identify our tangent and our chord. So our tangent would be r of m, and the chord has to touch the tangent. Okay, so now the chord that touches our tangent would be pl. The angle between our tangent and the chord, so the angle between this tangent and our chord in this case would be p1 is equal to the angle that the chord subtends. What does it mean to subtend? You're going to use that exact same method that I showed you previously. We're going to take, we're going to trace the lines from P all the way to the circumference of the circle. So remember, PL is our chord. We want to identify the angle that it subtends. We're going to trace it, trace it, trace it, ends over there. Do the exact same thing on the other side. We're going to trace it, trace it, trace it. It ends right over here at Q1. So we know that PL subtends Q1. So what does that mean? That means L1 equals to Q1. Okay, so we're just going to mark them off as being equal to each other. Okay, this is a very easy method, very easy. So you're going to mark them off as being equal to each other. We know that P1 equals to Q1. Okay, now let's continue on. We also have our other part of our tangent, Lm. Lm is a part of our tangent, forms a part of our tangent. Okay, so we've identified our tangent, in this case, our tangent, yeah, a part of our tangent is Lm. Then identify the chord that touches that tangent, it is Lq. The angle between the tangent and the chord is equal to the angle that the chord subtends. The angle that the chord subtends is angle P. As we can clearly see, why is that? Do the exact same thing. We're going to start off by tracing the lines that stem from the chord all the way to the other end of the circumference of the circle, the end over here. Do the exact same thing on the other side. Trace the lines all the way to the other end of the circumference of the circle. It ends over here. So we know that L5 is going to equal to P. And we just want to annotate them, mark them off as being equal to each other. I know there's a lot going on in the diagram, but it's so important to annotate. If you don't make annotations, you're not going to see any improvement in your Euclidean skills at all. Okay, so L5, I'm going to mark off L5 as being equal to P because of tan chord. Now we're done with tan chord. Let's move on. What about tangent perpendicular to radius? We need a tangent and we need a radius. Our tangent in this case would be RLM. However, the tangent, the radius has to touch the tangent. If the radius doesn't touch the tangent, then this theorem will not be valid. It will not be applicable. We've identified OL as being our tangent, and guess what? It actually touches our tangent. So this radius touches our tangent. What other tangent radius do we have? We have OQ, but the only difference between OL and OQ is that OQ does not touch our tangent. OL touches our tangent. So OL is the only radius that will help us use our tangent perpendicular to radius theorem. Okay, so the angle between our tangent and the radius will be equal to 90 degrees because of tangent perpendicular to radius. Okay, what does perpendicular mean? It means that the angle between two lines is 90 degrees. Okay, so now let's identify the angle between. I'm going to identify the angle. So let's first start off on this part of the tangent. So we have RL and we have OL. The angle between RL and OL would be L1 plus L2. So L1 plus L2 will equal to 90 degrees. Let's go over onto the other side. The angle between LM and OL would be L5, L4, and L3, meaning that L5, L4, and L3 will be equal to 90 degrees. Now, it's getting very, very complicated to see. It's very easy to, just be drawn. It's a lot going on, a lot of annotations, but yeah, that's not gonna sway us from annotating and understanding what's happening. Okay, so I'm just gonna mark them off as L5, L4, and L3, and L4 being equal to 90 degrees because of tangent perpendicular to radius. Now, we've explored and covered all of our theorems, but before we get started, this is one thing students always forget. You need to identify a cyclic quad. You need to go back and identify a cyclic quad. This is something that I'm always going to tell you, but you need to just remember this, okay? Now, um, now I do see a cyclic quad. We can see that And cyclic quad would be LQPN. When we think of a cyclic quad, we think of exterior angle of a cyclic quad, we think of angles in the same segment, and we think of opposite angles of a cyclic quad are equal to 90 degrees. Now, with this specific question, I can clearly see a bow tie shape. It is very evident that there is one. I'm going to go ahead and highlight it. So we have LN. I'm going to highlight LN. Sorry, I just want everyone to see exactly where the bow tie is. I know there's a lot going on, but just bear with me. Okay, so we can clearly see that L2 and L3 are in the exact same segment, and P and N are in the same segment. So I'm just going to mark them off. I'm not going to mark off Q2. I'm just going to remember, I'm just going to write that down, make an annotation, angles in the same segment, because it's really, there's a lot going on. But with P, I can definitely mark P as being equal to N, since we don't have as many annotations. So P is going to equal to N because of angles in the same segment. Now let's get started. 5.2.1 O2. What is the value of O2? Giving reasons. Now the great thing about actually making annotations is that sometimes you already know what the answer is before they've even ask you what the question is, before you've even received or read the question. Okay, so now O2, we know that O2, we're reminded of angle at center twice as much as angle at circumference, because we've marked off O2, um, O2 and P share the exact same arc. They're subtended but the exact same arc. But here is the catch: we need the numerical value of O2. So what you always want to do is, when you're working with and you have to calculate the numerical value of a certain angle, you always need to start on the part of you always have to start with the part of the diagram that actually has a numerical value. Let's start off with M. How can we connect M to O2? Now, the very first thing I want you guys to always think of, if O2 isn't directly equal to M through a Euclidean theorem, or if it's not indirectly equal to O2 through other angles through Euclidean theorems, always write down these theorems. Angles, sum of angles of a triangle, angles on a straight line, and vertically opposite angles. Now let's first start off with sum of angles of a triangle. Now, we want to first identify the triangle that O2 is a part of. I know you can't really see it, but look at that, guys. We can clearly see that it is a part of triangle OLM. Now, in order for sum of angles to work, we are going to need to know the numerical value of one other angle in the triangle. Everyone does remember that we said that L5 plus L4 plus L3, I've actually marked this off, it's in orange, you can't really see it. L5 plus L4 plus L3 is equal to 90 degrees because of tangent perpendicular to radius. Okay, so we know that L3, in other words, you could also name the angle as OLM, by the way. OLM is equal to 90 degrees, and we know that M is 26 degrees, so we could easily use sum of angles of a triangle to calculate what O2 is. And you need to weigh all options, guys. You need to test all options. I know a lot of students don't do this, but you have to do it. Okay, so we're gonna say O2 plus, we're gonna name it as OLM plus M equals to 180 degrees. Your reason is sum of angles of a triangle. Now, what is O2's value? That's what we're trying to look for, so we're just going to leave that out. What is OLM's value? It is 90 degrees, but you need to state that it equals to 90 degrees because of sum of angles of a triangle, or you're going to lose marks. What is M's value? We said it's 26. Then you're going to add those two values together, take it over on the other side, giving you an angle of 64 degrees because of angles in a triangle, sum of angles of a triangle. And what you want to do is you just want to go back and annotate this onto your diagram. I'm just going to annotate this and say that's 64. So yeah, so we don't have that much going on. Now let's continue on L2. What is the value of L2? We want to calculate what L2 is equal to. L2 is equal to P. Remember, we've marked off P as being twice as much. What does that twice as much represent? It represents the fact that P is equal to half as much as O2, and we already know what O2's value is, guys. It's 64. So you need to connect the dots. L2 equals to P, and P is connected to O2, which has a numerical value. You always need to use the part of the diagram with an actual numerical value. You need to use that as your starting point. So that's pretty straightforward, guys. So the very first thing is we want to calculate what P is. using angle twice as angle at center twice as much as angle at circumference. So we know that P's value is going to be half as much as 64, which is 32. So we know P is going to equal to 32, right? You just want to mark that off as being equal to 32. Angle at center equals to twice as much as angle at circumference. The next thing that you want to do is you want to mark off L2 as being equal to 32 as well, because of opposite angles equal sides. Okay, so you're going to see they're equal to each other. Angles opposite equal sides, and that is exactly how easy it is to calculate L2's value. Okay, now continuing on L5. What is the value of L5? L5, we've marked up L5 as being equal to P. Do you see the way everything just ties in together? Do you see the way everything just flows? We have no stops. The question is literally just flowing, guys. It comes natural to us because we've annotated, we've evaluated and assessed our diagram before we even started answering the question. So immediately we know 30 P is equal to 32 degrees. We know that L5 equals to P because of tan chord theorem. So you're going to mark off L5 as being equal to 32 degrees because of our tan chord theorem. Okay, on to the next question. What is Q1 equal to? Okay, so remember, guys, we've also marked off Q1 as we said Q1 and Q1 and O1 have the exact same they are subtended by the exact same arc. I remember we said this. So that's immediately what we think of. That's why it's very important to make annotations. We said that Q1 and O1 share the exact same arc, meaning angle at center twice as much as angle at circumference will be applicable. But the only issue is we have to find out, we have to calculate the value of O1. The minute we see, this is very easy, guys, we can clearly see that O1 is a part of an isosceles triangle. So if since we know that O1 isn't directly equal to another angle with tan chord, etc., we think of sum of angles of a triangle, we think of exterior angle of a triangle, and we think of angles on a straight line, we think of vertically opposite. But if the angle that you don't even have to list these options if you know that O1 is a part of isosceles triangle. Okay, we know what P is equal to, we know what L2 is equal to, so we're definitely going to use sum of angles of a triangle. Definitely. Okay, what you're going to say 32 plus 32 plus 1 equals to 180 degrees. Okay, O1's value is equal to 116. And now we can finally calculate what Q1 is equal to. Q1 is going to be half as much. You're going to take 116 divided by 2. So we can get to Q1 because of angle at center twice as much as angle circumference. And Q1's value will be equal to 58 for that reason. Okay, so you want to go back and annotate that as being equal to 58 degrees. And by the way, guys, they definitely use another method on the memo. The memo, they use sum of angles of a triangle because it's the exact same thing. Q1 is also a part of a triangle with more than enough information to use so that we can calculate what Q1 is. By the way, okay, we know they've used P is equal to 32. L2 plus L3 plus L4 is equal to 90 degrees. They've used the triangle. So you could use either method. They've used triangle PLQ. We can clearly see that angle L is equal to 90 degrees. We know that P is equal to 32 degrees, so you could have used sum of angles of a triangle to use Q1, but you could have also used my method as well. There are plenty of ways of doing this. Plenty of ways. Okay, so that's exactly how you'd get your answer. Now let's continue on to question 5.2.5. We have to calculate the value of n. Now this is very easy, very straightforward. We know that n is equal to p because of angles in the same segment. We've already marked them off as being equal to each other, and we know what p's value is. It is 32 degrees. Therefore, n will also equal to 32 degrees. So n equals to p, which equals to 30 degrees because of angles in the same segment. Okay, guys, hopefully this video was very helpful. Now please remember that it's very important, it's very crucial to go back over this question again, redo it again until you have a good understanding of it, until it flows as naturally as it did when I was covering the question in this video. Okay, and also, guys, your exam are in a few weeks. Okay, you need to take advantage of the time that you have. And also, we have our sessions each and every single day. We have daily sessions covering the questions that will be in your exam, guys. We've already conducted enough research. We've compiled a lot of questions with all of the questions that have been recurring, that have been asked in your exams, in your final exams for the past 6 years from 2015 to now. We've compiled a file of this and we go through that during our sessions. on a daily basis. Okay, so if you want to take advantage of having that privilege of going through the file with us together and to have a clear understanding on all topics in math and physics, not just Euclidean, make sure to send me an email so I can share more details. The email's in the description section. Other than that, we will see you in the next